All right, everyone, we're back. We're going to go through our final lesson of this unit, 3.4, Equations and Graphs of Polynomial Functions, Part 2. So for this first section, example 1 and 2, we're going to use what we learned from our transformations unit to see how we can sketch graphs or look at the characteristics and analyze the characteristics of a polynomial function. Okay, so here's the starting point. Let's read through a couple of definitions. Graphing polynomial functions using transformations. There's the general form of the transformation, right? So this should all start to look familiar with our A's, our B's, our H's, our K's. The effects of the changing parameters in the polynomial functions are the same as the effects of changing parameters in other types of functions. A is our vertical stretch about the x-axis by a factor of the absolute value of a. B is our horizontal stretch factor, horizontal stretch about the y-axis by a factor of 1 over the absolute value of b. H is our horizontal translation left or right. K is our vertical translation up or down. Okay, so remember to follow the SRT. So stretch, so when you're doing these analyses, so stretches, reflections, then translate. So unless told otherwise, do the transformations in that order when you're applying transformations. Okay, and then let's recall how to do mapping notation. Okay, transform the graph of y equals x cubed to sketch the graph of g of x equals negative 1/2 times 2 times x minus 1 in square brackets cubed minus 3. We start with our base function, y equals x cubed. Let's pick these points. So let's start off with that. Okay, 0, 0, 1, 1, 2, 8. Okay, let me put that down in a graph. Okay, and then our function looks something like this. Nice smooth curve. Okay. All right, y equals 2x cubed. So what happens when we put that 2 in there? Okay, so that's b equals 2. So our factor is 1 over, so 1 over the absolute value of b. So what does that turn into? Our factor is 1/2. Okay, and that's important. Let me write this a bit neater. I'm going to zoom in, folks. Okay, so our b value is 2. Okay, and our factor is 1/2. Remember, a factor for our horizontal stretch, this is our horizontal stretch, is 1 over the absolute value of b. Okay, so our factor means that we are multiplying the x values by 1/2. So if I go down here, let's do our mapping. So this is our mapping notation. Okay, for this first column, we're going from xy to 1/2 x and not changing the y. Okay? So if I apply the factor of 1/2, that becomes -1, -8. -1/2, -1. 0, 0, 1/2, 1, and 1, 8. Okay, next step. Y equals -1/2 times 2x in brackets cubed. So this is our vertical stretch. A equals -1/2. Okay, this one, I'm going to do two things. Vertical stretch and reflect in the x-axis. Okay, because I have that negative 1/2. Okay, what does that mean? I multiply all the y values this time. Okay, so recall our notation here. All the y values get multiplied by a. So let's go ahead and do that. So from the second column, negative 1 stays the same, and then that becomes 4. Negative 1/2 stays the same, that becomes positive 1/2, 0, 0, 1/2, negative 1/2, and 1, negative 4. Okay, last part. This is our translations. H equals positive 1, K, so we're going right 1 unit, and K equals negative 3, we're going left 3 units. Okay, so we're going to do two things at one time. So I'm going to take negative 1 and add 1, that becomes 0. And I'm going to take 4 and add negative 3, and that becomes 1. Okay, negative 1/2, I'm going to add 1, that becomes positive 1/2. And then 1/2, I'm going to add negative 3, that becomes negative 5/2. 0, 0, add 1, that becomes 1. Add negative 3 to 0, that becomes negative 3. 1/2 negative 1/2 translates to 1/2 plus 1, that's 3/2. And negative 1/2 plus negative 3, negative 7/2. And then 1, negative 4, 1 plus 1 is 2. Negative 4 plus 3 is negative 7. Something I forgot to do here is let's do our mapping notation. So next part, so this is for that vertical stretch and reflection. So 1/2 x, and then our stretch, vertical stretch and reflection. So this is original. This is horizontal stretch. This is two things, vertical stretch and reflect in the x-axis. And then this one finally is 1/2 x plus 1, h equals 1, and negative 1/2 y minus 3, k equals negative 3. So this is horizontal translate 1 unit right, vertical translate 3 units down. Okay, let's graph this. There's our original function. So if we graph this, I have, let me graph this in blue. 0, 1. Some of these points are going to be kind of hard to graph, so I'm going to do 0, 1. 1/2 negative 5/2, right about there. 1 negative 3, right about there. 3/2 negative 7/2 is right about there. And then I have 2 negative 7 right about there. So this one's going to look something like this. Nice smooth curve. And all the way down. Okay, so this one is y equals negative 1/2 in square brackets times 2 times x minus 1 square brackets cubed minus 3. Rewrite the equation for g in the form g of x equals a times x minus h to the third plus k. Okay, so I have g of x equals negative 1/2 2 times x minus 1 cubed minus 3. Okay, that's negative 1/2 times, I'm going to cube the 2, so that's 8 times, I'll leave the cube exponent 3 on the x minus 1 minus 3, and I have negative 4 x minus 1 cubed minus 3. Okay, example 2. Now, instead of graphing, we're going to describe the transformations that are happening just based on looking at the equation. Okay, so I have described the transformation of y equals x to the fourth to the graph of y equals 4 times in square brackets, negative 1/3, round brackets, x plus 2, close the round brackets, close the square brackets, all to exponent 4, and then minus 5. Okay, one by one. So I'm going to describe an SRT, stretches, reflections, translations. What is going on? So y equals x to the fourth. Let's first start with that horizontal stretch. Okay, so let's start with the horizontal stretch. That's transforming into y equals, so that stretch factor, or the b value is inside the brackets and where that exponent 4 is applied. So this leads to mapping notation x, y to 3x, y. So how do we do that? So first, this is a horizontal stretch about y-axis. Okay, how do I get a factor of 3? So b value is negative 1/3. Okay, and that's from our equation, negative 1/3. The factor, right, which is the number we use to do our mapping notation, is 1 over the absolute value of b. So that's 1 over absolute value of negative 1/3, and that just equals 3. So that's where we get this 3 value. Okay. Part 2, number 2. We take y equals 1/3 x to the fourth, and then we're transforming it with a vertical stretch of 4 let me write this properly. Okay, my mapping goes from so the previous one, 3xy, now maps to 3x 4y. Okay, this is a vertical stretch about the x-axis. Our a value equals 4, so where do we see that? There's our a value right here. A value equals 4. So remember, the factor is just the absolute value of a, and that equals 4. Part 3. Okay, we did the 2 stretches, horizontal stretch, vertical stretch. Now we're going to do the reflection. Okay, so we have the previous y equals 4 times 1/3 x to the fourth. We're going to transform that into y equals, the only thing we're changing, the only reflection we see is a horizontal reflection. So that b value is now turning negative. So what does that look like for our mapping notation? So from the previous number, number 2, 3x comma 4y, transforms to negative 3x comma 4y. Okay, so this is a reflection in the y-axis. Okay, because now our b value is less than 0. So our b value less than 0, there's that negative sign. B is less than 0. Number 4, our last transformation to apply are the translations. So y equals 4 times negative 1/3 x to the 4th. We're translating that to y equals 4 times negative 1/3 x plus 2, close the brackets, exponent 4 minus 5. H equals negative 2. Okay, and then k equals negative 5. H equals negative 2. Horizontal translation, 2 units left. Okay, k equals negative 5. Vertical translation, 5 units down. Okay, globally, our mapping notation here. We had, from the previous example, negative 3x, 4y. That translates to negative 3x minus 2, comma, 4y minus 5. Okay, globally, what does it look like? So we started with xy. So number 1, we started with xy. Sorry, the original. And then in number 1, we applied our horizontal translation. It mapped to 3xy. So this is our horizontal stretch. Number 2, vertical stretch. Three x, 4y. Number 3, that's our reflection. So reflect in the x-axis, or sorry, in the y-axis. Okay, and then the last one, 4. Okay, this is translate 2 units left. Sorry, that should be a U. 2 units left. Translate 5 units down. Okay. The horizontal stretch. Let me just go back. B equals negative 1/3, and the factor applied is 3. Vertical stretch. A equals 4. So the factor is 4. For the reflection in the y-axis, b is less than 0. Okay, so b is equal to negative 3. And then the last one, translate 2 units left, that's h equals negative 2. and translate 5 units down, that's k equals -5. Okay, next page. Application of polynomial functions. Example 1, Bill is preparing to make an ice sculpture. He has a block of ice that is 3 feet wide by 4 feet and 5 feet long. Bill wants to reduce the size of the block by removing the same amount from each of the 3 dimensions. He wants to reduce the volume of the ice block to 24 cubic feet. State a polynomial function to model this situation. So let me draw a picture first. Here's a block of ice. Okay, there's my block of ice, nice rectangular prism. It's 3 feet by 4 feet, so 3 feet wide, 4 feet high, and 5 feet long. Okay, Bill wants to reduce the size of the ice by removing the same amount from each of the 3 dimensions. So this is what we're doing here. He wants to remove same amount from each dimension. Okay, so this amount would be x, this amount would be x, this amount would be x, this amount would be x. Okay, so you can imagine shrinking this block down, cutting out the, so I'll just shade it in here, cutting out this back side here. So we're cutting out the back. We cut off the back, and then we're going to shave off this part all the way down this way, right? Okay, so we're going to get a smaller block. That looks like this. I'll try to keep the proportions similar. Okay, so algebraically speaking, the new width is 3 minus x. Algebraically speaking, the new height is 4 minus x. And algebraically speaking, the new depth, or the length, is 5 minus x. State a polynomial to model this situation. Okay, and we said the new block of ice is 24 cubic feet. So remember, the volume of a rectangular prism is length times width times height. Okay, volume is 24. That's the desired volume. 5 minus x times 4 minus x times 3 minus x. State a polynomial function to model this situation. There you go. All right. Part B, determine algebraically how much he should remove from each dimension. Okay, let's start with 5 minus x times 4 minus x times 3 minus x equals 24. And then I need to multiply all this out. Okay, so what do I got? I got 20 minus 5x minus 4x. Okay, you got the idea. Let me just get through this. Okay, let me group everything to the left side. So I'm going to subtract both sides by 24. So I get 36 minus 47x plus 12x squared minus x cubed equals 0. Negative x cubed, let me just write it in descending order of degree. Okay. All right. I need to solve for x. How do I factor this thing? Or how do I solve for x? Remember, I have to use synthetic division. Okay, find some factors. So out of 36, right, you have all the possible integral zero theorem. I have all the possible zeros in there. I'll just make the work a little faster for you. You can try a whole bunch, but x minus 1 works. So I'm going to divide by x minus 1. So remember, if I do x minus 1, that is x minus a. I'm going to use a equals 1 for my synthetic division. Okay? So let's do that. So I have 1, and then my polynomial, negative 1, 12, negative 47, and 36. Okay, let's do some synthetic division. Okay, awesome. We get a remainder of 0. Okay, so we know x minus 1 is a factor. Okay, so this is negative x squared plus 11x minus 36 equals 0. I'm going to factor out a negative 1. And I'm left, I'm solving for x, right? So I have divide both sides by negative 1. I have this. Can I factor that? What multiplies to 36 and adds to negative 11? 1 and 36, 2 and 18, 3 and 12, 4 and 9. This is telling me I need to use the quadratic formula. So x equals negative 11 plus or minus negative 11 squared minus 4 times 1 times 36 over 2 times 1. That's positive 11 plus or minus 121 minus 144. Ooh, I know what's going to happen here. Look at the discriminant, right? Discriminant is less than 0. Remember that? Review, Math 20-1. Right? Delta is less than 0. What happens, right? Let me just simplify this a little bit. So this is a non-real solution, not useful for us, right? We need real solutions, real numbers, because we're talking about a block of ice. It cannot have imaginary or complex number solutions, right? So my roots, real and non-real, let me just list this way, are x equals 1. So remember, I gave that to you in the beginning here. X equals 1. And x equals 11 plus or minus square root of negative 23 over 2. I'm going to ignore the non-real ones. I need a real root. X equals 1. Okay, let's check this. I have 5 minus x times 4 minus x times 3 minus x equals 24. Let's plug in 1. And 4 times 3 is 12 times 2 is 24 equals 24. Left side equals right side, so my solution is x equals 1. Well, what is that? 1 foot of ice to be removed from length, width, and height to get a volume of 24 cubic feet. Okay, last part, verify with technology. Okay, so if I'm starting with this equation, okay, when I graph this, I'm going to say y1, I'm going to use the intersection method. y1 equals 5 minus x times 4 minus x times 3 minus x. And then y2 is just a horizontal line, y2 equals 24. Okay, find intersection point, x value is solution. Okay, let's do that. So try that, pause here, try this on your graphing calculator. My window, I have 0, 10, 1. Okay. And this is what my screen would look like. So there's my three, 4, and 5. So it's going to look something like this. So down 3, 4, and 5. Okay. And then so this is y2 equals 24. And obviously in blue, this is y1. Okay, and then the intersection point, this point I get is 124. And then the x value, x equals 1 foot, is my solution. Last page, folks. Yes, almost there. Okay, word problem. 3 consecutive integers have a product of negative 210. State a polynomial function to model this situation. What does consecutive mean? So integers first of all. Okay, that's an integer. Consecutive integers, like -1, 0, 1 are consecutive. 1, 2, 3 are consecutive, right? So one right after the other. So if I say let x equals an integer, what's the consecutive one? Consecutive means the next one. So the next one, either to the right or to the left. Let's just go to the right. We're adding 1. Next consecutive. X plus 1 or x plus 2. And it says 3 consecutive integers have a product. Product means multiplication. So x times x plus 1 times x plus 2 must equal negative 210. Okay? You could have done x minus 1, and x minus 2. Doesn't matter which way consecutive you go, you're going to arrive at the same answer. Determine algebraically the 3 integers. Okay, so I'm going to have to multiply this out. So x times x plus 1, x times x plus 1 times x plus 2 equals negative 210. Okay, let's expand and simplify. And then let's make everything equal to 0. Remember, we need to solve for 0 to solve for x, right? It's 210, right? You're going to have to look for factors of 210 using the integral 0 theorem. I'll just make it quick for you. X plus 7 works, so a negative 7. Let's do some synthetic division. Okay. Okay, remainder is 0 as we expected. This is x squared minus 4x plus 30 equals 0. You can't factor it, so I'm going to use the quadratic formula. Okay, x equals negative 4 plus or minus negative 4 squared minus 4 times 4 times 1 times 30 over 2 times 1. Okay, I got x equals positive 4 plus or minus 16 minus 120. Uh-oh. Discriminant is less than 0. What happens? Over 2. There's a solution, but it's a non-real solution, so I'm going to ignore that. Okay, and then go all the way back. This is x plus 7. So x equals negative 7 is your solution. Okay, let's check our answer. Okay, x equals negative 7. So x equals negative 7. Let's check. Okay, we're still going to multiply it out to check, but these are consecutive, right? So it's looking good. Okay, so negative 6 times negative 5 is 30 times negative 7 is negative 210 equals negative 210. Left side equals right side to check. Okay, let's graph this. It says check with technology. My x window, negative 10, 10, and 1. My y window is negative 5, 10, 15, 30, and 1. Okay, I'm going to use the intersection method. Where y1 equals x times x plus 1 times x plus 2, and y2 equals negative 210. Okay, this is what my window looks like. That's y2 equals 210, negative 210. And then my y1 value looks like this. Okay, it is a cubic function. This is y1. Okay, and then I have an intersection point right here. This is -7, -210. X equals -7. Okay, let's make sure we have to determine the three integers. Okay, almost forgot to do that. First integer, this is the first integer. Second integer, x plus 1 equals -7 plus 1 equals -6. That's the second integer. And x plus 2 equals -7 plus 2 equals -5. That's my third integer. Okay, -7, -6, -5. Okay, I lied. This is actually the last example. Investigating non-real zeros. Okay, consider the fourth degree polynomial p of x equals x to the fourth minus 5x squared plus 8x minus 12. The polynomial can be written in factor form as p of x equals x minus 2 times x plus 3 times x squared minus x plus 2. So we've done the heavy lifting and factored it for you. Use the factor form of p of x to state two real zeros of multiplicity 1. Well, here's our two real zeros. X equals 2, x equals -3. Solve the equation x squared minus x plus 2 equals 0 using the quadratic formula to show that the other two zeros are non-real. Okay, let's do it. Quadratic equation. Discriminant is less than 0. Non-real solutions. So the solution doesn't exist in the real number world. It exists. It actually exists. It's still a solution, but it's a non-real solution. It exists in the imaginary complex number realm. Okay, so that's actually beyond the scope of this course. But how do we treat it, or how do we recognize it in a graph? Letter C. Graph p of x, x to the fourth minus 5x squared plus 8x minus 12 using a graphing window right there. Indicate on the graph how the non-zero roots appear. So this is what I get when I graph this. So here's my window. And this is what I get. Okay, let me mark where the zeros are. So there's my window of -5. And then -3 is right there. Okay. And then my window of +5, 1, 2, 3, 4, 5. And that's my 0 of 2. So each multiplicity 1. Okay, when I graph this, what does it look like? Oh, let me just complete the window there. 1, 2, 3, 4. Okay. Starts out here. Reaches a minimum. Comes back over. And then it goes straight up through the 2. Okay. Sorry, let me correct that. That should be non-real. Okay. How do the non-real roots appear? First off, the real roots are right here. Okay. real roots highlighted in green. Okay, good. How do the non-real roots appear? So let me write a little explanation here. Our non-real roots are, so let's restate it from the top here. 1 plus or minus -7 over 2. These numbers are considered complex numbers of the form, again, this is just for your information, but this is beyond the scope, of the form a plus bi and cannot be represented on a Cartesian plane. So a Cartesian plane is our xy plane, Cartesian plane. If you're interested, go Google how do I graph complex numbers, and you'll see some great YouTube videos on visualizations of how complex number solutions look for functions like this. It's actually quite fascinating. Okay. So, but since you can't graph them, they are represented in the Cartesian system as something very telltale, right? So I'm going to put a little asterisk here. And then let's highlight this little part right here. Right there. Look for inflection point. And then let me just start over here. This turning point indicates, turning points indicate, the presence of non-real roots. The key here is that if you remember from a multiplicity, let's say of an odd number multiplicity, so multiplicity of 3, something like x minus 3 times x minus 3 times x minus 3, right, a cubic, that's going to produce an inflection point, but that's through the x-axis. The difference with a complex number solution or a non-real solution, this turning point happens without crossing the x-axis. Okay, so let me just write this out. The graph changes direction without crossing the x-axis. Okay, turning point. It hasn't crossed the x-axis right here. It turns before it crosses the x-axis. Okay? Note, if a real polynomial function has non-real zeros, then non-real zeros always occur in pairs, which are conjugates of each other. This form, where q, the discriminant, is less than 0. So our solution here, pairs, and they're conjugates. Okay? Non-real zeros are also known as imaginary zeros or complex zeros. Okay? So examples, the graphs below represent polynomial functions which have non-real zeros. Indicate A, the region on the graph which represents non-real zeros. Turning point, inflection point, concave up, concave down, but does not cross x-axis, and it's my turning point. Okay, that's all you need to know. Okay. Write a statement which describes the number, type, and multiplicities of 0. First, let me go through where the turning points are. Okay. Right there. So non-real zeros. Turning point right here. Non-real zeros. Okay, and this one, whoa, lots going on here. Turning point right there. Non-real zeros. And again, look, turning point, have not crossed the x-axis. 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 Write a statement for each which describes the number, type, and multiplicity of zeros. Okay, let's go. So for graph 1, 1 real 0. Okay, I'll mark it in red right there. 1 real 0. Multiplicity of 1. Okay, 2 non-real zeros. Let me call them, zeros. Multiplicity of 1 for each. Okay, 2. 1 real 0. Oh, actually, I have 2 real zeros, and they're just multiplicity of 1 each, right there and right there. Each has a multiplicity of 1, and then I have 2 non-real zeros, multiplicity of 1 for each. 3 1 real 0. There it is right there. Multiplicity of 1 and 2 non-real zeros. Multiplicity of 1 for each. And then 4. There's a 0, there's a 0, there's a 0. Okay. 1 real 0 has a multiplicity of 2. Okay, that's the bounce one, so multiplicity of 2. Okay, and then I have 2 real zeros, each with a multiplicity of 1. Okay, and then 2 non-real zeros, multiplicity of 1 for each. Okay, and now we're done.